Once we have these, we can go to our second step, right? This was just the definition of an operator that came after learning about changing our perspective or changing our coordinate system. The third step in any symmetry argument is to connect things back to the Hamiltonian. So connect back to H. Now, when we connect these back to the Hamiltonian, we've already been through this argument. We know how, for any operator, we know how to figure out what the Hamiltonian looks like in the flipped coordinate system. And when we insist that the Hamiltonian must be the same in the new coordinate system, which we know it must be in this case for rotations, we immediately had the consequence that, in fact, the Hamiltonian must always commute with the generator of whatever that particular change in coordinate system is. So my Hamiltonian, I know, then actually will commute with all three of these different infinitesimal rotation operators. So that must be zero. That's the reflection of symmetry in quantum mechanics. So that's directly by symmetry. It might be a little more interesting, though, to relate this commutator to what we know are physical quantities, namely these angular momenta. So let's make that connection now by inserting our definition for these rotation operators, which are all just the identity minus I times the corresponding component of the angular momentum operator, x, y, or z, times, of course, the rotation angle, then all divided by h bar. Now, we've worked with commutators before, so we know, for instance, we can separate out the commutator as a sum. So then I have to add the commutator of h with this piece. But, of course, also constants can simply be pulled out of commutators because those actually commute with all of our operators. So I'd have minus I epsilon over h bar times then the commutator of my Hamiltonian then with any of my angular momentum components. And finally, we know this commutator is zero because the identity operator doesn't care which side of h it's put onto. And because all of this actually now equals zero, I can divide both sides through by these constants. And my final conclusion then is that the Hamiltonian actually therefore commutes again with any component of the angular momentum operator. That commutator will be zero, and this then has all kinds of important implications as we had discussed before when we had looked at the parity symmetry. Some of these implications are, for example, that it's possible, not guaranteed, but it's possible that we can find a state where the uncertainty in the Hamiltonian times the uncertainty in any of these angular momentum components, right, could be zero, right? The Heisenberg uncertainty principle says that this has to be greater than or equal to zero, but it's possible that those are zero, so that it's possible that pure states of angular momentum might also be pure states of H. So maybe pure H's are, pure energy states. I'll put it this way, pure with respect to H are also pure with respect to any of these angular momentum components. That's at least possible from the Heisenberg uncertainty principle. We, of course, have not proved this yet, but that's kind of nice. The other thing that we know is that the angular momentum is conserved. Because by the general Ehrenfest theorem, I know then that the time derivative of the expectation of any of these operators, right, which would be, of course, the expectation of 1 over I h times one of the times these commutators, which are all zero, those things then never change as well. So this is a beautiful set of results for our angular momenta.